Hello, this is a talk about specification and complexity of replicated objects. Replicated objects are a formal way of capturing the behavior of replicated data stores. These are large-scale distributed systems running Google, Facebook, Amazon, etc. We want these systems to provide lots of things, in particular, most importantly, high availability. This means that we can get a response without communication with servers that are far away from us, only by communicating with the close-by, almost local replica of the server. So for example, if the World Health Organization is putting out a notification about what to do about coronavirus, they want to have an immediate response from the nearby server, and the latency should be very quick, and this should happen even if the network is for some reason not operating correctly and is partitioned. Later, these updates are propagated to the other servers, and eventually they should converge to the same state, a property called eventual consistency. So in this talk, what I'll do is provide a theoretical exploration of highly available replicated data stores. I will provide a framework for considering and studying them as asynchronous message passing implementations of shared objects. And I will present results for the achievable consistency they can provide and for the message size and metadata overhead for providing their services. A well-known result in this area is that no data store can provide the following three properties simultaneously. It cannot be both strongly consistent, highly available, and partition tolerant. So strong consistency means that it provides a property similar to serializability and above. Namely, there's a way to, there's a reference sequential execution of all the operations that happen on the data store. High availability means that responses are immediate, and partition tolerance is that the responses are correct and immediate, even if there is no communication in the system between the replicas. So the proof is actually rather simple, and it uses this execution that is on the slide. Basically, it's an execution of two replica and two variables. I represent different variables, different registers with different colors. So there's the blue variable and the green variable. And the first replica writes to the first blue variable and then reads from the green variable. And the second replica does the converse thing, writes to the green variable and reads from the blue variable. Now, if we have a strongly consistent system, then the two writes to the blue variable and the green variable must be ordered somehow. So for example, assume the write to the blue variable is before the write to the green variable. Note, however, that it is possible that the system is disconnected. There's a partition between replica 1 and replica 2. So when the read by the second replica from the blue variable happens, it does not communicate with replica 1. And in fact, it gets the old value, the initial value, value 0 from, for the blue variable. Okay? And the same on the other side. It's possible that, replica 1 does not receive any message from replica 2, so when it reads the green variable, it returns 0. Okay? However, we have to order the two writes in a strongly consistent system. And of course, we have to preserve the per-replica order. So this means that somehow we put, say, the write to the blue variable before the write to the green variable, which means that it's not possible that the read from the blue variable will return the initial. So that's kind of the proof for the CAP theorem in a nutshell. And this led the researchers and system builders to concentrate on weaker consistency properties. And one of the things that were done is to expose concurrency. So basically, when we have concurrent and conflicting writes, even to the same register, same variable, then we expose them to the reader and we tell to the client and say, well, these are the two possible values, you pick your choose. So if, for example, replica 1 writes 1 to the blue variable and replica 2 writes 2 to the blue variable, then it's not clear what's value to return and what value to return to to a read. And under strong consistency, under an ordinary variable, we would have to resolve this conflict and return some value. But sometimes what we do is actually we just expose this conflict to the user. Systems like Dynamo does that. And they support what's called the multi-valued register, which basically tells the reader, well, these are the two values that were written concurrently, you make your choice. Now note that in order to talk about which values are concurrent and visible and observable by the reader, we were talking about what was returned and the messages that were sent and what was delivered to the node. And the problem with that is that it's mixing high-level and low-level details. So it's mixing a discussion talking about messages sent in the system with information about values that must be returned, about high-level operations. And that's not a great thing, and it's not a good way to do specifications. It exposes too many details. And further, it allows implementations to fictitiously, vacuously preserve specification by, say, not doing anything and not sending any messages, etc. So a way to avoid this mess is basically to extend, take further the idea of the reference execution that we have in serializability. So basically, we have a reference execution that is not sequential, unlike serializability, but it's still abstract enough. So basically, we specify replicated object using visibility relations over abstract executions. This is a notion suggested by Buchard, Gotsmani, and Konsolowski. So what's an abstract execution? Basically, it's an execution that only contains high-level events. So here, for example, we have 3 replicas, one writes to the blue variable, another writes to the blue variable, and writes to the green variable, and the third actually reads from both variables. And a visibility relation is just any relation over these events, as long as it has 2 properties. One is that it's acyclic, and the second, that it respects the per-replica order. So, for example, here we have the write by replica 1 to the blue variable is before the write by the second replica, and so on. And if we look at the order that I've drawn here, we see that because of acyclicity and because of the per-replica ordering, the read from the blue variable must return 2 because it precedes, it follows the write of 2, and the write of 1 is before the write of 2. Now note that visibility is not message delivery. We don't know which messages were delivered in this execution. Visibility is a possible explanation that is consistent with a possible set of message deliveries, but we don't know what happened because this is not a concrete execution. This is an abstract execution, so we don't know which messages were sent or delivered in this execution. And once we have this visibility relation, we can say what is a correct response for an operation, basically by looking at the operations that are visible to it. So, for example, as I said, the read has all 3 2 writes two writes that are visible to it, and basically it can, if it's a multi-valued register, it can return any of them. Okay. So if the visibility relation includes a link, an edge between orders the write of 1 before the write of 2, then the read must return only 2 because the write of 1 is before the write of 2, so it's not visible. The second write hides it. And if we don't put this edge in the visibility relation, then the read must return both values. So both values are possible values. And once we have the abstract executions, we can talk about concrete executions, like what actually is implemented, what happens in the implementation. And a concrete execution implements the object, or it is a correct implementation of the object if it complies with some abstract execution of this object. So again, this is similar in many ways to serializability. The serializable execution is correct if there is some sequential execution. And complies basically says, it means that it has the same responses at each replica. Okay, so basically, we look at the concrete execution and we require that there will be an abstract execution and a visibility relation that explains it. And a consistency model basically is a prefix-closed set of abstract executions and their visibility relations. And an implementation satisfies a model if each of its concrete executions complies with some abstract execution of the model. So the common consistency model that is used, that is kind of weaker than serializability, but is still meaningful and useful, is called causal consistency. This is a notion that was introduced by Hagit Attiya in the early 90s. And basically it says that if an operation is visible, so are all the operations it depends on. So if some operation observes, or if some operation is visible to another operation, then all the operations that preceded the first operation are visible to it. So for example, if this is the visibility relation that we have, then it must be that R1 observes the first write to the blue, that the read from the blue variable observes the write of 1 to the blue variable. So basically, causal consistency is nothing but saying that the visible relation must be transitive. And in fact, in this way, we can add causality to any object specification in a very smooth and convenient way. An interesting thing about causal consistency is that it's considered to be the strongest thing you could provide with highly available system. And one of the results I want to show you, and was one of the motivations for this work, is to see whether this is indeed the case. So in order to explain what such a result means, I need to explain what it means to be the strongest possible consistency model. So how do we compare consistency model? And basically, if we have fewer abstract executions in the model, then it is stronger. Might sound kind of counterintuitive, but really, if we have fewer abstract executions, there are fewer possibilities for the behavior of the system. Okay? And because of that, as programmers, as clients of the system, we will have fewer things to worry about. And in some sense, the system, the consistency model, is actually simpler and easier to work with. So stronger. So in particular, causal consistency allows more abstract executions than serializability, and hence it's weaker. So serializability is stronger than causal consistency. As I said, causal consistency is a very popular causal consistency model. It's provided by several systems like IO and COPS and others. And as I said, it's a question whether causal consistency is the best, the strongest consistency model that can be provided. And in order to answer this question, we cannot answer it in isolation from the liveness condition that the system must provide, the data store must provide. And the most common consistency liveness condition is eventual consistency. Despite being called consistency, it's not really a consistency model. It's a well-known notion that has been in use in various ways for many years, but it was made popular in a paper, in a CSM paper by Werner Vogels. And in this paper, he has this the following definition. It's a specific form of consistency. The storage system guarantees that if no new updates are made to the object, eventually all accesses will return the last updated value. So first of all, know that this is a liveness property. Eventually something good happens. Also know that it's actually very restricted. It gives you a guarantee only if at some point the system becomes acquiesces. Okay? So if the system, if there are continuous updates to the system, there's actually no guarantee whatsoever about convergence. That's not ideal. However, we can use the notion of abstract execution and visibility relations to specify eventual consistency. was done by Buchart et al. In paper. So basically, an infinite abstract execution is eventually consistent if an operation is invisible only to finitely many operations. So only a finite number of operations may be unaware of a specific operation. And eventually, it must become visible to all the operations, to all operations. So if we continue like looking and reading at the state of the object, eventually every update will be visible to us. And it implies Vogel's informal definition as a special case. So the theorem we prove is that an eventually consistent data store cannot satisfy a consistency model that is stronger than observable causal consistency. So observable causal consistency is a model slightly stronger than causal consistency. Okay. So basically, the theorem says that the best you can get with eventual consistency is almost causal consistency, somewhat a little bit stronger, which actually we don't know how to achieve, to be honest. So there's a slight open question here. And observable causal consistency basically resolves the ordering of operations and hides concurrency between them, unless the user can somehow learn that these operations were unordered. So unless basically there's an equivalent abstract execution in which they are not ordered. So it's a very technical definition, and but roughly it says that causal consistency is the best you could hope for. We also prove a theorem about the size of messages that are needed to ensure causal consistency, and essentially it says that the best you could do is use vector clocks. Okay? So, which is a very well-known implementation technique to ensure causality. So the exact statement is that if n is the number of replicas and s is the number of multi-valued registers, each of them may hold up to log k bits, k values, then some message, when we implement the causally and eventually consistent data store, some message must be of size the minimum between n and s times log k in terms of bits. Which essentially means that you must use vector clocks if the number of variables is larger than the number of replicas. And it's an open question what happens when s is much smaller than n. I will not show the lower bound. It has a very nice proof technique, which is based on encoding and decoding state from the execution. And I'll talk more about the similar technique or an application of this technique in the context of another lower bound that I will show later at the start. So this completes the first part of my talk. In the second part, I want to move to more interesting data stores, which store shared documents. So, for example, Google Docs or wikis of types, of all sorts. And such systems allow us to store shared documents so that several clients in several locations working with the different replica of the data store, of the shared object system, can edit this document together. So for example, my running example will be these three chefs. Ismail Aroni is a famous Israeli chef, Julia Child, famous American chef, and Olvera, who's a Mexican chef. And they all are working together to write a recipe for something. As before, under the hood, what we want is high availability. So whenever one of them makes a change to the document, they want to get a response or to know that their change was safe without waiting to communicate with the other replicas. So for example, if Aroni wants to put the line fry onions, because it's a good way to start any recipe, it will get an immediate response from its local server in low latency. And then this change will later be propagated to the other servers. And similarly for the other chefs. And again, this should happen even when there are partitions. Okay, now a shared document has more structure than the read-write variables, even the multi-value variables that we've seen before. So Aroni writes this line, its update is propagated. Eventually, we want to converge to the same document. What does it mean to converge to the same document? So the basic object that we look is a basic document editing. Has basic document editing operations. It has elements, which could be words or lines. And we have three operations. One is an insert, the other is a delete, and finally a read of the state of the list. So an insert inserts an element at some particular position. We assume that elements are unique. And a delete deletes an element, and a read returns the state of the list. And basically, besides the read that returns the state of the list, also every other operation returns the state of the list. So when I do an insert, I see the document. When I do a delete, I see the document after the delete, etc. So for example, if I insert X at position 0, basically for an empty list, I get back the list X. And if I then insert A at position 1, basically after X, I get XA as the state of the list. So what does it mean to return the state of the list? I get a list of elements, each of which was previously inserted, but not previously deleted. So you should now pause and look at this and ask yourself, what does it really mean to be previous? Because we have a big system, deletes, inserts, etc., modifications, updates are happening across the world, so to speak, Mexico, the US, Israel, and how do we order these updates? And of course, we don't want to rely on low-level information about execution. So we don't want to rely on message deliveries or received. So we turn back to the solution we had in the earlier part of the talk and rely on visibility relations in abstract executions. So basically an implementation, in an implementation of the list object, every concrete execution of the implementation must comply with an abstract list execution. And basically each operation returns an ordered list of elements such that each element has a visible insert and does not have a visible delete. So let's go back to the example, the scenario with Aroni and other chefs editing their documents. So Aroni inserts this line of frying the onions into the document, and this is propagated to some server in Brazil. And Olvera sees this and says, oh, these onions are frying, so let's now mix them with mushrooms. And this is sent also to this server in Brazil. And then Child also sees this line and says, hey guys, you cannot fry onions without chopping them first. Okay, so she inserts this line, chop onions before the frying the onions and the mixing with mushrooms. Okay, so Child and Olvera saw the intermediate state of the document with the line of fry onions. One of them wanted to insert a line after frying the onions, another wanted to insert a line before frying the onions. Right. Now, Aroni looks at this document and says, what, frying onions? No, 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 I don't want to have I have second thoughts about that. Frying is bad for your health, and it's fatty, and it makes bad smell in my quarantined house. So I want to remove this line. So it sends this line that it sends a delete of this frying the onions, and the line gets deleted from the store, the shared document. Now the updates of childs and Olvera are in progress, are being propagated to join the document. And when they arrive, the line of frying the onions that was used to order them is no longer them. So it is possible that the line of chopping the onions arrives and is put at the end of the document. And then the line of mixing them with mushrooms arrives and frying the onions is not there. So it's put at the beginning of the document. So we get a reordering of the lines. And that's a bad recipe. You cannot mix onions with mushrooms and then chop them. And actually, some systems may give you this result, but you don't want it. So how do you specify that it doesn't happen? How do you rule out this behavior? And the way you do it is with what's called the strong list specification. So basically, the strong list specification provides, in addition to the other properties, the visibility relation that we had, it provides an irreflexive relation that is transitive and total on all inserted elements. So basically, there's a total order on all elements inserted ever in the execution, not just the current set of operations. The current set of elements in the list. And the intuition is that we are remembering deleted elements and using them to order elements that are still in the list. So in our example, we have the insert by Aaroni and followed by the delete. And then we have, following this insert, the insert by child, and then the insert by over. And then later the delete by Aaroni. And the result we want to have is that the A inserted by child will be before the B inserted by over, although the X that was used to order them is no longer there. Now, this will be ensured by the strong list order because the order will be that A is before X and B is after X. And then if we return AB, then there's the relation is A before B, which is fine, this is cyclic. But if for some reason we'll return B before A, then we'll have a cycle. And the strong list specification will disallow this response. Okay, and interestingly, there's an algorithm for the strong list specification. It's called the replicated Growable array, RGA. And what it does, it represents the set of elements, the list state as a tree. And basically, elements that are inserted at the same position are resolved or ordered using a timestamp that is assigned dynamically. And the way the strong specification is provided is by keeping tombstones for deleted elements. Let me explain a little bit about the algorithm and then about tombstones. So, as I said, we use kind of a tree representation to store list content and timestamp metadata. Each element is basically the element, each node in the tree is basically the element and a timestamp. And basically the way we read the list is in prefix order. So I read the node and its children, a node and its children, and so on and so forth. And all the children of a particular node appear in decreasing timestamp order. So for example, if I want to insert position K, I just pick a large timestamp, larger than all timestamps currently in the system. And then I insert the new node as a child of the immediately preceding element. So if I want to insert B, the timestamp T4, after X, what I'll do is I find the node for X, and then I insert B, the timestamp T4, which is larger than everything in the tree, as a child of X. And I send out the new node. And if I have concurrent insertions at the same position, they are inserted as children of the same node, and eventually they are propagated. So the node has both of them, but somehow there's some arbitrary order between the timestamps, and when the list is printed out, it is always printed in the same order, in the same timestamp order. And to delete, it's very simple. Okay. What we do, we find the element and we just mark it. And that's what's called leaving a tombstone. where the item was. So whenever we get to an item that is deleted, we know that it's there, but we don't print it out as part of the list. Now, this means that there's a lot of garbage in this tree, and it's even worse because in shared editing systems, changes are modeled not as like changes in place, but it's actually as deletion and insertion of the revised or modified element, which means that any change creates a tombstone, and that's bad. So you ask yourself, is this necessary to keep all these tombstones? And it seems that the answer is no. Okay. So indeed, the answer is no. There are implementations like treedoc, logroot, that each element has a position, which is a sequence of edge levels. You may think that this is basically a denotation of the path to this node in this tree. And however, the label is not compressed. So if I got inserted very deep in the tree and my label reflecting my position is very long, it doesn't get compressed, even if all these nodes on the path were deleted. And there are also implementations based on operational transformation, not quite well known, but there you log the updates and keep the log, the growing log all the time, and then you do transformations and modifications to recreate the final state of the list. So you avoided nominally having tombstones, but you didn't avoid their cost. Okay, so still all these algorithms, all these implementations keep a lot of metadata. And metadata, the metadata overhead is defined to be the size of the list state divided by the size of the observable list. So if I have a small observable state, okay, that I kept a large state information, then my metadata overhead is very big. So can the metadata overhead be avoided by some different way of implementation? And the answer is no. So there's a lower bound on the metadata overhead, which says that there is an execution with d deletions in which some replica has omega of d bit metadata overhead. The lower bound holds even if the underlying message passing system provides causal atomic broadcast. It also works for a weaker specification of the list object, which I will touch upon in a minute. And so these are the upsides. The downside is that it works only for what we call push-based protocols. And these are, I would say, aggressive protocols that whenever they have an update, they send it. And whenever they get an update, they process it. Okay, they merge it into their current state. So that's the metadata lower bound. And to prove the lower bound, we use, as I mentioned before, an encoding technique. So we are going to show that there's an execution in which the list state at some replica at the end of the execution just contains one character, an asterisk. However, the state of the replica has omega of the bits. And the way we demonstrate this execution is by encoding arguments. So we show that for each d-bit string W, we can construct an execution alpha W with the following properties. First of all, in alpha W, there are some replica performs d deletions without receiving any messages. And at the end of the execution, the state of the list at this replica is the asterisk. Okay, so just one character, one element. However, despite the state having just one value, just one element, still we could decode what W was. Okay, so looking at the state of the replica, we could decode what the W was. And the reason we can decode is because we should be prepared to lots of changes. The replica should be prepared to be able to handle many changes to the execution, to the state of the list. We also have that the replica has no pending messages, outgoing messages, because we say that we are not hiding information in the message records. So because there are 2D such strings, and because we can decode the string from the state, it means that the size of the replica state at the end of the execution must contain at least unbounded digits. So the actual proof is non-trivial, quite interesting, and I recommend reading it. This almost completes my presentation. So as I mentioned, the result also holds for a weaker specification, actually where the acyclic order does not have to hold for all the elements ever inserted to the list, and just to elements returned at each particular instance. This corresponds somehow from a model where servers are not equal. One of them could be a master, and the others are clients, and are not peer-to-peer. And we don't know if for peer-to-peer systems, the weak specification is equivalent to the stronger specification. The weak specification captures some real systems, like the Jupyter algorithm that underlies Google Docs. It was proved after the original publication of our paper. So to conclude, I've presented a systematic study of replicated data stores. There are still lots to be done. For example, tighten the consistency result, because we proved just for OCC and not for causal consistency. Message size bound also can be tightened for the case that S is smaller than N. And the metadata bounds are also, are far from the actual, not far, but still not tied to the actual complexity of these algorithms. It would be nice to remove the assumption of push-based protocols, or to get better algorithms that violate them. A very interesting topic is garbage collection, because we assume that there's no like offline or asynchronous process thread in the servers that can go around, ask what's happening, and remove some of the information that are maintained at the server. And of course, it would be nice to go beyond plain text editing to share documents that support more interesting operation like spreadsheets and etc. This is the last slide. Thank you for listening. This talk is based on 2 papers, both with Adam Morrison from Tel Aviv University and these other references.